So you know that thing where you're making a gin and tonic at 3 in the morning because you have a problem, and then all the lights in your house go out and your sleep paralysis demon shows up next to you holding a UV light and shines it at the tonic water, causing it to glow? Yeah, me neither. Although since we're on the topic, let's talk about fluorescence. But before I get to the rest of the video, why not hit that subscribe button? Because having more subscribers might give me an incentive to make videos more frequently instead of the several months I have been doing. And now on to fluorescence. So to understand fluorescence, I need to talk about the electromagnetic spectrum and spectroscopy. Now, you've probably seen a diagram of the electromagnetic spectrum before in a textbook somewhere. It looks like this, with radio waves on one end and gamma waves on the other. And spectroscopy is essentially the study of how matter reacts when you hit it with photons of light. Think of it like if you're at a batting cage and the pitching machine breaks and starts rapid firing baseballs at you, and someone is off to the side with a clipboard making note of how the baseballs bounce off of your body and maybe looking at the baseballs that don't hit your body. That's kind of what spectroscopy is, except instead of baseballs in your body, it's photons in any substance. Anyway, the part of the spectrum that I'm going to be focusing on for fluorescence is the visible and ultraviolet portions of the spectrum. But to fully explain fluorescence and how it works, I need to talk about different types of molecular motion and how molecules can store energy. And starting off simply, there's translational motion, which is basically, moving something from one point in space to another. So I'm here in this shot, and now I'm over here. That's sort of translational motion. Although things get slightly more interesting when we bring in rotational motion, because a molecule isn't just, fixed, unmoving, and just kind of like moving about. It can rotate, usually around the three coordinate axes, the x-axis, the y-axis, and the z-axis. And so a molecule can rotate about those three axes, and depending on basically how fast it's rotating, it can have different levels of energy of rotation. Although even more important than rotational energy is vibrational energy, because a chemical bond isn't, a rigid stick that is unmoving. It's flexible, it can move. Think of it a lot like a spring. In fact, a lot of the physics used to describe springs are also used to describe chemical bonds. And so a good way to sort of understand how chemical bonds can vibrate is to look at a molecule of water. And it's very easy to do because I can use my own body to sort of represent that, with my torso being the oxygen atom and my hands being the hydrogen atoms. And so if I stick my arms out like this, I can kind of represent a water molecule. And my arms being the chemical bonds between the atoms, you can see the vibrations where you have symmetric stretching where the bonds are compressing and stretching at the same time, or asymmetric stretching where one bond is compressing while the other is stretching. And then you can have, a bending vibration where the sort of bonds don't necessarily stretch or compress, but rather, wiggle back and forth. And so that's kind of, how chemical bonds can vibrate. They can stretch, compress, or bend. And now that I've covered molecular motion, I can talk about energy levels and transitions between those levels, because the fundamental principle of most spectroscopy is that if you hit matter with a photon of light, it's going to excite that matter from one energy level to the next, whether that be rotational, vibrational, or in this case, for fluorescence, electronic transitions. See, any given molecule has electron orbitals. I've sort of talked about this before in a previous video, but those molecular orbitals are made up of the atomic orbitals from each atom that makes the molecule. Makes sense, right? Although for the purposes of this video, we're really only concerned with what's known as the frontier orbitals, the highest occupied molecular orbital and the lowest unoccupied molecular orbital, known as the HOMO and the LUMO. So generally speaking, when a molecule is hit with a photon of ultraviolet or visible light, it will excite an electron from the HOMO into the LUMO. And after a period of time, usually in the span of like nanoseconds, that electron will relax back down into the HOMO and re-emit a photon of light. So now it's time to actually talk about fluorescence after however many minutes of me rambling about molecular motion and energy levels and electron orbitals, as I am one to do. So ultraviolet visible or UV vis absorbance spectroscopy focuses on the light that is, get this, being absorbed by a molecule, whereas fluorescence focuses on the light that is being emitted by a molecule. And this is why you can say that absorbance and fluorescence spectrums of the same molecule are going to be mirror images of each other. And what's actually pretty cool is that fluorescence is fairly common in everyday life. If you've ever seen something glow under a black light, that's fluorescence, because a black light is just a UV light and things that glow are fluorescing because they have some molecule that's a part of them that fluoresces. Although when it comes to fluorescence, it's important to note that the wavelength of light being emitted is going to be slightly different than the wavelength of light being absorbed. And to understand why that's the case, I'm going to make a rather simplified Jablonski diagram. And not just because Jablonski is a fun word to say, even though it sounds like an insult someone from Philadelphia would shout at me. So to start, I'm going to put a big line at the bottom of the diagram. This represents the electronic ground state of a molecule, and this next part is why I mentioned vibrational and rotational motion earlier, because every electronic state has its own set of vibrational energy levels, and each of those vibrational levels has a set of rotational. So this is the ground state, and above this is some excited electronic state, again with the vibrational and rotational energy levels associated with it. So when hit with the right wavelength of light, an electron will be excited from the ground state into this excited state. And this is where the vibrational levels are important because the electron won't necessarily be in the ground vibrational state. So what happens is the molecule undergoes what's called vibrational relaxation, where the vibrations relax naturally without emitting any photons. Then the excited electron finally relaxes back down to the ground state. But because it relaxed from a lower vibrational level than it was excited to, the emitted photon has slightly less energy than the one used to excite the electron, thus giving it a longer wavelength. And now I'm going to actually show you what fluorescence looks like. I'm going to be using a UV light that I have for curing resin 3D prints, as well as a very sophisticated device that I designed myself. A box with a hole cut in it. What side? This side. A box with a hole cut in it so I can stick a camera in there. And we're going to start with the classic example of tonic water, because tonic water contains a molecule known as quinine or quinine, or I'm not entirely sure how to pronounce it. I like to say quinine. And quinine is a molecule that fluoresces, thus tonic water fluoresces. And you can't really see it as well in the video, but if you look at the surface of the water, you can actually see the fluorescence taking place. And to give a more interesting example for the camera, I have a container from some toxic waste candy that fluoresces quite nicely. See that nice glow of the plastic? And while I'm not entirely sure of this, but I am like 99% sure, that glow is because the plastic contains some compound that is fluorescent. Well, that's going to be it for this video. If you made it this far, thank you so much for sticking with it. I know this kind of topic isn't necessarily something that everyone's going to be interested in, but I enjoy talking about it, and I'm hoping that my enjoyment of it will help other people enjoy it. And who knows, if this video does well enough by my channel's standards, maybe I'll make more videos talking about different kinds of spectroscopy. Again, thank you for watching. Subscribe if you're not already, and I will try to make sure my next video is something other than me rambling about chemistry for however many minutes.